96% of their bullets were hitting nothing but air, not occasionally, not as a failure mode. Consistently, systematically. Every single day over Europe and the Pacific, thousands of American gunners were firing hundreds of thousands of rounds at enemy aircraft and missing almost all of them. The mathematics were so brutal that military analysts initially thought their data was wrong. They rechecked it, reviewed gun camera footage again, ran the numbers a third time. The results didn't change. By 1943, trained American aerial gunners, men who had completed rigorous training, who had practiced extensively, who had every motivation to hit their targets, were achieving hit rates below 4% against crossing targets. In a typical 10-second engagement where a Browning M2 could fire roughly 130 rounds, perhaps 5 bullets would actually strike the enemy aircraft. 5 hits from 130 rounds. That's not marksmanship failure. That's not a lack of courage or commitment. That's physics declaring that human intuition is completely wrong when dealing with objects moving at 300 miles per hour. The problem had a name: deflection error, and it was about to kill tens of thousands of people before anyone figured out how to solve it. But here's the thing that nobody expected. The solution wouldn't come from better equipment. It wouldn't come from longer training. It would come from understanding that human brains are fundamentally incompatible with the speeds of aerial combat, and that the only way to win was to train people to do something that felt completely wrong. The story of deflection shooting is the story of a military crisis that nobody saw coming, a physics problem that nobody knew how to solve, and a solution so counterintuitive that it took actual combat losses before people would believe it worked. It's the story of how you train someone to aim at empty sky and trust that their bullets will hit metal, and it changed everything, from World War II fighters to the F-22 Raptor to the missile systems, protecting aircraft carriers right now. The problem started with an assumption that seemed perfectly reasonable. When you want to hit something with a bullet, you aim at it. You point your weapon at the object you want to strike. You pull the trigger. The projectile travels from the barrel to the target and impacts. This is how rifles work on shooting ranges. This is how hunters shoot deer. This is how every human has ever thought about hitting something with a projectile. Aim at the target. The target gets hit, but aerial combat operates under different rules. Rules that human intuition never evolved to handle. Rules that didn't exist for 99.9% of human history. In 1943, when American bomber gunners were encountering these rules, they were encountering something their training hadn't prepared them for because their training couldn't prepare them for it. The physics were too counterintuitive. The speeds were too extreme. The available time was too short. A Zero fighter approaching at 300 miles per hour covers 440 feet every single second. At a typical combat range of 300 yards, 900 feet, a .50 caliber Browning M2 bullet needs approximately 0.31 seconds to travel that distance. The muzzle velocity is roughly 2,900 feet per second, which sounds fast until you do the math and realize that 0.31 seconds is an eternity in aerial combat. In those 0.31 seconds while the bullet is in flight, the enemy aircraft moves another 136 feet. That's 11 car lengths. That's nearly the entire length of a football field. The gunner aims where the aircraft is. The bullet arrives where the aircraft was a third of a second ago. Empty air. The enemy fighter continues untouched. This happened over and over and over again. Gun camera footage from 1943 missions shows the pattern repeatedly. Initial bursts with some forward lead, followed by progressive bursts walking backward as the gunner visually corrected what he thought was leading too much. He was self-correcting in exactly the wrong direction, trusting his eyes over the physics he couldn't see. If you're realizing that this is a story about how human intuition can betray us at the worst possible moment, and how one counterintuitive technique could double kill rates in just 8 weeks, hit that subscribe button, because what comes next is going to blow your mind. Drop a comment on whether you would have figured out that aiming at empty sky is the solution. And keep watching because the answer involves some brilliant physics and some equally brilliant psychology. The statistics were apocalyptic. In 1943 alone, the 8th Air Force flying bombing missions over Europe lost approximately 1,400 bombers. That's roughly 116 per month. Each B-17 carried a crew of 10 men. That meant approximately 1,160 air crewmen were being killed, captured, or going missing every month. Many of those deaths occurred specifically because the bomber formations couldn't effectively defend themselves against fighter attacks. They had guns. They had ammunition. They had trained gunners. But they couldn't hit anything. The psychological impact on crews was catastrophic. You're flying in formation at 25,000 feet, oxygen mask fogging, temperature 50 degrees below zero, knowing that German fighters are coming. Your only defense is the gunners in your aircraft. Then you watch those gunners fire thousands of rounds while enemy fighters penetrate the formation untouched. You watch bombers explode around you. You realize that the defensive fire you're relying on for survival is completely ineffective. The October 1943 missions to Schweinfurt and Regensburg were particularly brutal. 60 bombers failed to return out of 291 dispatched, a 20% loss rate. Survivors landed with dead and wounded crewmen, shredded hydraulic systems, engines trailing smoke. The crews reported the same frustration in debriefings. The guns were working. The ammunition was flowing, but the bullets weren't connecting. By 1943, it was clear that something fundamental was wrong with how America was training its aerial gunners. The Army Air Forces had established the Flexible Gunnery School at Laredo, Texas in 1942. They put students through rigorous programs. Trainees spent hours in turret simulators. They studied diagrams showing proper lead angles. They shot at towed targets being dragged behind trucks. Some received as little as 4 weeks of training before being deployed to combat. By late 1944, that had expanded to 8 to 10 weeks of training with 5,000 practice rounds instead of 1,000. But the fundamental problem remained. You could teach the mathematics of deflection in a classroom. You could show students the diagrams. You could even have them practice shooting at moving targets on the ground. But when they got into actual combat, under stress, facing enemy aircraft that were trying to kill them, most of them reverted to instinct. They aimed at the visible target. They watched their bullets miss, and they lived long enough to repeat the mistake again. The technical problem was clear. Deflection error. Against a target crossing at 90 degrees at 300 yards distance, a gunner needed to aim approximately 15 to 20 feet ahead of the aircraft's nose. That meant putting your crosshairs on what looked like empty sky. Completely empty. No visible target. No obvious point of aim. Just empty space that hopefully contained the future trajectory of an enemy fighter. Every human instinct screamed that this was wrong. Every natural instinct suggested that leading that far ahead would result in an even worse miss. The brain said, reduce the lead. Get the target visible in your sights. Trust what you can see. The physics said, stop trusting what you can see. The target won't be there. Lead farther. Trust the mathematics. The problem was that human brains evolved to throw spears at animals moving at 20 km/h, not to aim at fighters moving at 300 plus imap. The cognitive systems that had kept humans alive for 200,000 years were fundamentally incompatible with the speeds of modern warfare. If this realization about the gap between human intuition and physical reality is starting to grab you, the idea that our brains can be catastrophically wrong about high-speed problems, hit that like button and keep watching. Drop a comment on whether you think the solution would come from better training or better equipment. And keep watching because MIT was about to create something that proved there was a third option nobody had thought of. The solution had been sitting in a filing cabinet since 1924, not forgotten, not buried, just waiting. 20 years before the crisis became obvious, military theorists had recognized that as aircraft speeds increased, the deflection angles required to hit them would become so large that conscious calculation alone couldn't handle it. The solution wasn't to train human brains faster. The solution was to build a machine that could do the calculation. The flexible gunnery school at Laredo had been trying to solve the problem through training, extended programs, more practice rounds, more realistic target scenarios. By late 1944, they'd created a particularly effective method: motorized turrets firing at targets being towed by high-speed boats at 50-60 mph, while the distance and crossing angles varied randomly. Gunner trainees engaged these targets repeatedly, 50 to 70 passes per training day, until the act of leading became automatic. It was training that bypassed conscious thought entirely, embedding deflection correction at the same neurological level as walking or catching a thrown ball. This required thousands of practice rounds and weeks of intensive training, but for the gunners who got it, muscle memory took over. Under stress, their hands maintained proper deflection automatically even when their conscious minds were terrified. But there was a parallel track running at MIT. Charles Stark Draper's team at the Radiation Laboratory Division 7 was building something different. Not a training solution, a mechanical solution. They were creating a machine that could solve the deflection equation in real time. The Mark 14. Gyro Computing Gunsight was a mechanical computer. Inside, the sight housing were gyroscopes, spinning spheres maintaining precise orientation through pure physics. Cams, carefully shaped pieces of metal that converted input into output angles, and mechanical linkages that continuously updated the firing solution as variables changed. The gunner would track a target normally, moving the turret to keep the enemy aircraft in view. The sight's gyroscopes would continuously measure the rate of turret movement. The cams would convert that rate information into real-time deflection corrections. The result: the sight's reticle would automatically position itself at the precise lead angle required to intercept the target. The gunner didn't have to calculate anything. He didn't have to estimate. He aimed the sight's reticle directly at where he saw the target, and the mechanical computer behind the reticle positioned his bullets where the target would be. Navy testing at Norfolk in 1943-44 showed the results. Gun camera footage before the Mark 14 showed hit rates hovering around 5%. With the computing sight installed, hit rates jumped to 15 to 25% within the first few weeks of implementation. A 3 to 5-fold improvement in effectiveness. That meant fewer bombers shot down. That meant fewer crews dying. That meant the bombing campaign would actually achieve its objectives instead of collapsing under casualties if this story about a mechanical computer doing something the human brain couldn't do is starting to show you the fundamental difference between training and equipment, and how sometimes you need both. Hit that subscribe button right now because the implications extend far beyond World War II. Drop a comment on whether you think equipment or training mattered more for solving the deflection problem. And keep watching because the real revolution came when they combined both approaches. The transformation from 4% hit rates in early 1943 to 20% plus by late 1944 wasn't caused by any single solution. It was caused by a combination of 3 separate innovations converging at exactly the right moment. First, there was the understanding of the physics. The mathematics of deflection had existed since the 1920s, but military doctrine hadn't incorporated it into training. By 1943, that understanding was finally being translated into training methodology. Second, there was the equipment solution. The Mark 14 computing gunsight was revolutionary because it removed the conscious calculation requirement. Gunners who used it didn't have to understand the math. They just had to use the sight. Third, there was the training evolution. The Flexible Gunnery School and the Naval Air Gunner School at Jacksonville had figured out how to embed deflection correction into unconscious competence through repeated practice at realistic speeds with immediate feedback. Each approach had advantages and limitations. The Mark 14 was perfect for scenarios where you could track targets systematically, but production limitations meant only a fraction of aircraft could be equipped. Training was universal. Every gunner could benefit, but it required time and ammunition that didn't always exist. The combination produced results that neither could achieve alone. By 1944, elite gunners who had survived 30-plus missions demonstrated something remarkable in combat footage analysis. Their deflection aim points remained stable even under extreme stress. When a FW-190 came screaming through the formation with cannon fire flashing from its wings, these experienced gunners maintained their lead automatically. Their conscious minds could be absolutely terrified. Many admitted to being convinced they were about to die. But their hands kept the proper sight picture anyway. They'd achieved what martial artists call mushin, the state where technique happens without conscious direction, where the body knows what to do because the body has done it 10,000 times before. But that level of proficiency took time and ammunition most gunners never received. The mathematics of wartime were brutal. If creating an expert deflection shooter required 5,000 practice rounds and 10 weeks of intensive training, but the bomber offensive needed 50,000 new gunners in 6 months, compromises were inevitable. Most gunners flying combat missions never achieved true unconscious competence. They remained in the conscious competence stage, capable of proper deflection when conditions allowed them time to think, but vulnerable to collapse under stress or when facing unexpected situations. This created a strange stratification in combat effectiveness. A bomber formation's defensive capability wasn't uniform. It depended entirely on which specific gunners were in which specific positions. A formation that happened to include several veterans with deep training could fight off attacks that would devastate a formation of newer crews. German fighter pilots learned this quickly. They targeted bombers that showed hesitant or inaccurate fire during initial passes. They avoided formations where the defensive fire was immediate, heavy, and precisely placed. If you're realizing that this is a story about how training and equipment need to combine, and how human skill matters even when machines are helping, hit that like button and subscribe, because the lessons extend far beyond World War II. Drop a comment on whether you think modern pilots still need to practice deflection shooting, and keep watching because the answer might surprise you. The Mark 14 computing Gunsight became the foundation for every deflection solution that came after. After the war, it evolved into the Mark 18, which served through the Korean War. Then digital fire control computers emerged, capable of processing dozens of variables simultaneously. By Vietnam, fighter aircraft carried radar-assisted gun systems that calculated deflection automatically. Pilots only had to keep targets within acquisition parameters. The F-4 Phantom's lead computing optical sight did in fractions of a second what had taken Draper's mechanical gyroscopes significant time. Modern air-to-air combat has largely moved beyond guns entirely. Missiles handle interception at ranges where deflection would require leading by miles. But the underlying principle hasn't changed. An AIM-120 AMRAAM missile uses inertial guidance and active radar to continuously update its trajectory toward where its target will be. It executes deflection calculations thousands of times per second. The F-22 Raptor's AN/APG-77 radar doesn't just track targets. It predicts future positions based on current velocity and acceleration. It positions the aircraft and selects weapons accordingly. Same problem that WWII gunners struggled with. Same solution. Calculate where the target will be instead of where it is. Just implemented with computers processing terabits per second instead of gunners manually estimating angles. What's remarkable is that deflection shooting fundamentals remain part of modern fighter pilot training. Despite guns being tertiary weapons in contemporary air combat, the Navy Fighter Weapons School, Top Gun, still teaches basic fighter maneuvers that include guns-only engagements. Not because pilots expect to dogfight with cannons. Modern combat happens at beyond visual range where missiles dominate. But deflection shooting training develops spatial awareness that applies to every aspect of air combat. A pilot who's mastered leading a maneuvering target intuitively understands closure rates, angle off, and lead pursuit curves. Concepts that matter whether firing a cannon or positioning for a missile shot. The training carries forward. The lessons extend beyond aviation into every domain involving fast-moving targets. Modern anti-aircraft systems, like the Phalanx CIWS protecting naval vessels, are essentially sophisticated implementations of what WWII gunners struggled to do manually. The Phalanx fires 4,500 rounds per minute, 75 rounds per second, at incoming missiles and aircraft. Its radar continuously calculates deflection and updates aim point. It makes the same corrections bomber gunners needed in 1943, just faster and without the human hesitation that cost so many lives. Even video games that simulate combat incorporate deflection mechanics, teaching the same counterintuitive principle. War Thunder and Digital Combat Simulator require players to lead moving targets manually. New players experience the exact same frustration WWII gunners felt, watching their tracers arc harmlessly behind enemy aircraft until they internalize that leading is necessary. The most skilled players develop the same unconscious competence that combat veterans achieved. Their hands adjust aim without conscious thought. They've internalized the principle through thousands of repetitions with immediate feedback. If this evolution from WWII deflection, shooting to modern F-22 systems to video game training is showing you how one solved problem becomes the foundation for centuries of innovation. Hit that subscribe button right now and turn on notifications. Drop a comment on whether you think WWII soldiers would be amazed or unsurprised by modern automated deflection systems. And keep watching because the final piece of this story is about what the deflection shooting problem teaches us about human adaptability. The psychological barrier to deflection shooting was just as deadly as the technical one. In 1943, when gunnery instructors first tried teaching deflection shooting to bomber crews, they encountered something unexpected. Even when students intellectually understood the concept, even when they'd practiced it repeatedly, they couldn't maintain it under stress. The human brain has an overwhelming preference for what's called pursuit curve logic, the idea that if you're trying to hit something, you maintain your aim directly on that something. It's how predators hunt. It's how we throw balls at moving targets. It's been hardwired into human neurology for hundreds of thousands of years. Combat introduced a variable that training couldn't fully replicate. Terror, gun camera footage from actual missions shows this progression repeatedly. An enemy fighter enters a gunner's field of view. The gunner begins firing with proper deflection, aiming ahead of the target. The initial bursts show tracer rounds arcing well in front of the aircraft. But then something happens. Perhaps the gunner sees his bullets passing in front of the target and concludes he's leading too much. Perhaps the stress of incoming fire causes his brain to revert to pursuit curve logic. Perhaps the acceleration of the enemy aircraft or his own aircraft creates an unexpected change in relative velocity that breaks his mental model. Whatever the cause, gunners progressively reduced their lead in subsequent bursts. The camera footage shows this clearly. The tracer pattern walking backward, from ahead of the target, toward the target, and eventually behind it. The gunner was self-correcting in exactly the wrong direction, walking his fire backward from an effective solution toward a position of increasing ineffectiveness. By the time the engagement ended, typically 8 to 12 seconds, the gunner's final bursts were often aimed directly at the target's current position or even behind it. Empty misses, the only gunners who maintained effective deflection were those who'd already gone through approximately 50-70 simulated engagements with realistic speed moving targets and who'd achieved what psychologists call automatic processing. Their conscious minds didn't have to make the calculation anymore. The correct lead angle was embedded in muscle memory, or RAF. Fighter Command discovered this principle independently through a series of experiments in 1940-41 by Squadron 609. After early combats against the Luftwaffe showed poor effectiveness, RAF commanders had pilots study skeet shooting technique. The principle behind hitting a moving clay pigeon was identical to hitting a fighter aircraft. You had to lead the target. But skeet shooters had been solving this problem for decades through practice and feedback. The RAF pilots who participated in the skeet shooting training program showed measurably improved effectiveness in subsequent combats. Hit rates roughly doubled. The explanation wasn't that skeet shooting taught better aim. It was that skeet shooting taught instinctive, deflection correction at the neurological level where muscle memory operates, this insight that deflection correction could be learned at an unconscious level through sufficient repetition, became the foundation for training programs that actually worked. If you're realizing that this story isn't just about physics but about human psychology, about how terror and stress cause us to abandon learned skills, and how the only antidote is to make the skill so automatic that stress can't override it. Hit that like button and subscribe. Drop a comment on whether you think stress affects your own decision-making in high-pressure situations. And keep watching because the story of how one particular training innovation created that automatic competence is remarkable. The breakthrough in deflection training came from an unlikely place: the understanding that you can't train someone to perform well under extreme stress by practicing in calm conditions. By late 1944, the Naval Air Gunner School at Jacksonville, Florida had developed a particularly effective training system. They mounted 50 caliber guns on motorized turrets that could spin and elevate rapidly. Then they had high-speed boats tow targets across the water at speeds up to 60 mph, while the distance and crossing angles varied randomly. This wasn't predictable practice. Gunner trainees couldn't anticipate what the target would do next. They just had to engage it, check their hit pattern, adjust, and engage again. The innovation wasn't the equipment. It was the insight that training needed to create the same cognitive load as combat. The trainees engaged 50 to 70 passes per training day. That's thousands of rapid-fire decisions under time pressure with immediate feedback about success or failure. What makes this approach remarkable is how it bypassed conscious thought entirely. Instructors didn't correct students verbally during the drills. They simply had them shoot, check the hit pattern, and continue. The feedback was immediate and objective. The student could see exactly where his bullets went. The brain's learning systems adapted to this feedback loop faster than conscious instruction could possibly work. After weeks of this training, something remarkable happened. Trainees who engaged actual enemy aircraft in combat reported that their hands just knew where to aim. Their conscious minds might be terrified. They might be convinced they were about to die. But when they tracked an enemy aircraft, the proper deflection correction happened. Automatically, this is what neuroscientists call procedural memory, or implicit learning, knowledge that's retained in the body and nervous system rather than in conscious declarative memory. It's the same mechanism that allows you to ride a bicycle even after years without practice, or to catch a ball without consciously calculating its trajectory. The tragedy of WWII gunnery was that only a fraction of combat gunners received this intensive training before deploying to combat. The mathematics were brutal. If each gunner required approximately 5,000 practice rounds and weeks of intensive training to achieve automatic competence, and the bomber offensive needed 50,000 new gunners every few months, there simply wasn't enough ammunition, training capacity, or time. Most gunners deployed to combat after 4 weeks of training and 1,000 practice rounds. That was enough to make them consciously competent, capable of proper deflection shooting when they had time to think about it. But it wasn't enough to make deflection correction automatic. Under stress, when conscious thought broke down, these gunners reverted to pursuit curve logic. They aimed at what they could see. Their bullets missed. If you're realizing that this is a story about how training has to match the demands of reality, and how insufficient training cost lives in ways that had nothing to do with courage or commitment, hit that subscribe button right now and turn on notifications. Drop a comment on whether you think modern military training still makes this same mistake. And keep watching because the story shifts. Now to what happened when one small group of experienced gunners proved how effective deflection shooting could actually be. The data that finally proved deflection shooting worked didn't come from theory or laboratory testing. It came from combat footage analysis of the most experienced gunners. After 3 years of war, there were gunners who had survived 30, 40, 50 combat missions. Statistically, this was almost impossible. The casualty rates were so high that most combat gunners were killed or wounded before reaching 10 missions. But a small percentage survived, and those survivors had something remarkable in common. They were devastating to German and Japanese fighter pilots. When analysts reviewed gun camera footage from engagements involving these experienced gunners, the pattern was unmistakable. Their deflection aim points remained stable. When a FW-190 came screaming through a bomber formation with cannon fire flashing from its wings, these veteran gunners maintained their lead angle automatically. Their conscious minds could be absolutely terrified. Many debriefing reports mentioned gunners convinced they were about to die, but their hands kept the proper sight picture. Anyway, they'd achieved automatic competence. More remarkably, German and Japanese fighter pilots learned to identify bombers defended by inexperienced versus experienced gunners. They'd probe a formation with initial attacks, observing the quality of defensive fire. They'd deliberately target bombers that showed hesitant or inaccurate fire. They'd avoid formations where the defensive fire was immediate, heavy, and precisely placed. This created a bizarre situation where a bomber formation's survivability depended not on the total firepower available, but on the distribution of experience within that formation. A group of 10 bombers with 3 highly experienced gunners, distributed among them, might survive attacks that would devastate a formation of 10 bombers with only novice gunners. Fighter-pilot interviews after the war reveal a clear awareness of this phenomenon. Experienced Luftwaffe pilots described encounters with certain American formations as shooting galleries, where defensive fire was so ineffective that attacking the formation was relatively low risk. They described other formations as extremely dangerous, where the defensive fire was so heavy and accurate that attacking required luck. The difference wasn't equipment. Both formations had the same guns. The difference was training and experience. By 1944, as the extended 8 to 10-week gunnery training programs began producing more experienced crews, and as the Mark 14 computing gunsight was distributed to more aircraft, the overall combat effectiveness improved dramatically. Hit rates that had hovered at 4 to 5% in 1943 were reaching 15 to 25% by late 1944. The improvement rippled through the entire bombing campaign. Fewer bombers were shot down. Fewer crews died. Bombing missions that might have been aborted due to unsustainable casualties continued. Strategic bombing, which had seemed on the verge of becoming impossible due to attrition rates, suddenly became sustainable if you're realizing that this is a story about how experience, combined with training, creates something neither can produce alone, and how the distribution of expertise through a formation matters as much as the total amount. Hit that like button and subscribe. Drop a comment on whether you think modern military units understand how crucial experienced personnel are. And keep watching because we're about to explore what happened after the war when this knowledge was supposed to be preserved and instead was almost completely lost. One of the great tragedies of military history is how often hard-won knowledge is lost between conflicts. Deflection shooting revolution of WWII was one of those cases. The principles that had been so painfully learned through thousands of casualties were understood by the veterans who survived. But as those veterans left military service and transitioned to civilian life, much of that knowledge dispersed. By the Korean War, 1950-53, deflection shooting had to be relearned. The Mark 14 computing gunsight had evolved into the Mark 18, which served with distinction. But the training principles that had been so effective in WWII were not automatically passed down to the new generation of fighter pilots and gunners. The result? Pilots and gunners in Korea showed similar learning curves to their WWII predecessors. Early engagements showed lower effectiveness. As experience accumulated and training methods improved, effectiveness increased. The progression was similar to what had happened a decade earlier. By Vietnam, the cycle seemed to be repeating again. American fighters were equipped with radar-guided missiles that were supposed to eliminate the need for gun combat entirely. But the missiles had lower effectiveness rates than expected, particularly against enemy aircraft that could maneuver unpredictably. Combat footage showed that experienced pilots, those who'd survived multiple engagements, were scoring at significantly higher rates than novice pilots. The Navy eventually reactivated advanced training programs, including Top Gun, established 1969, which reincorporated many of the principles that had been so effective in WWII. The training emphasized realistic combat scenarios, moving targets, and the development of instinctive reactions rather than conscious calculation. The results were striking. American pilot kill ratios improved dramatically. By the end of the Vietnam War, experienced American pilots were achieving kill ratios against North Vietnamese fighters that approached the effectiveness of WWII bomber gunners who'd received extended training despite fighting in a completely different environment with different aircraft and weapons. The lesson that kept being relearned: training that creates automatic, unconscious competence through repeated practice in realistic, high-stress conditions produces dramatically better results than training that focuses on conscious knowledge. If you're realizing that we keep making the same mistake in every conflict, underestimating how important training is, losing knowledge between wars, having to relearn hard lessons at the cost of lives, hit that subscribe button right now and turn on notifications. Drop a comment on what military knowledge you think we've lost since Vietnam. And keep watching, because the final section of this story is about how modern systems have finally solved the deflection problem completely. Or have they? The mechanics of the Mark 14 computing gunsight reveal why mechanical solutions worked where human calculation had failed. Inside, the gunsight housing were spinning gyroscopes, maintaining precise angular orientation through pure physics. These weren't electronic devices. This was mechanical engineering at its finest. Precisely machined spheres rotating at thousands of revolutions per minute, creating angular momentum that resisted external forces according to the laws of physics that had been understood since Newton. The gunner would track a target using conventional methods, moving the turret to keep the reticle on the approaching aircraft. But now the gunsight's gyroscopes measured how fast the turret was moving, not by calculation, but by physical resistance. The rate of turret movement created forces on the spinning gyroscopes that could be measured mechanically. Cams, carefully shaped pieces of metal, converted this rate information into deflection corrections. A cam is essentially a mechanical function generator. As a shaft rotates through different angles, the profile of the cam determines how much a follower mechanism moves. The shape of the cam mathematically encodes the relationship between turret tracking speed and required deflection angle. When a gunner tracked at one rate of speed, the cams positioned the reticle at the correct deflection correction for that speed. When the tracking speed changed, the cam position changed, continuously updating the aim point. The genius of this system was that it was entirely automatic. The gunner didn't have to calculate anything. He didn't have to estimate. He simply maintained the reticle on the target, and the mechanical computer handled all the physics in real time. Navy testing in 1943-44 showed the results weren't subtle. Before the Mark 14, hit rates around 5% in actual combat conditions. With the computing sight, hit rates jumping to 15 to 25% within weeks of implementation. Gun camera footage showed the difference. With the computing sight, tracer fire arced to where the target would be. Without it, the tracer fire passed behind the target's current position. The improvement was so dramatic that it couldn't be attributed to better training or gunner experience. The same gunners using the same guns with the computing sight achieved 3 to 5 times better results than without it. This created a fascinating technical and tactical situation. The Mark 14 gunsight was revolutionary. But production capacity was limited. Turret guns in bomber aircraft were designed before the computing sight was invented. Retrofitting existing turrets took time. Many aircraft that desperately needed the technology didn't have it. By 1944, newer aircraft entering service had the Mark 14 installed from production. But older aircraft that had been flying missions since 1942 often didn't. This created another stratification in combat effectiveness, not just between experienced and inexperienced gunners, but between gunners with mechanical computing aids and gunners without them. Analysis of loss rates by aircraft type and equipment configuration shows the dramatic impact. Bombers equipped with Mark 14 gunsights showed consistently lower losses to fighter attack than identical aircraft without the gunsights. The difference wasn't due to differences in crew quality or training, both types of aircraft were being crewed by graduates of the same gunnery. Schools, if you're realizing that this is a story not just about training and physics, but about how technology and training interact, and how technological solutions can sometimes substitute for extensive training. Hit that like button and subscribe, because what comes next shows how these principles scaled far beyond World War II. Drop a comment on whether you think technology or training is more important. And keep watching. The astounding thing about deflection shooting principles is how they appear independently in completely different military contexts, suggesting that humans keep reinventing the solution because they don't preserve knowledge. Medieval crossbow makers understood lead compensation when targeting moving targets. They tested bows extensively and developed mental models about compensating for target motion. This knowledge was embedded in the craft of bow making, but never formally codified. Naval artillery instructors in the late 1800s developed sophisticated calculations for firing at moving targets. The principles were well understood. Gunnery schools taught deflection computation. But this knowledge somehow didn't transfer effectively to the air warfare domain when it emerged after 1903. The reason is organizational. Each military domain developed its expertise independently. Naval gunnery experts didn't realize the problem they'd solved was identical to the problem aerial gunners faced. Aerial gunnery experts, seeing a new problem in a new domain, thought they were facing something unprecedented. By the time the connection was made in 1943, thousands of people had died from not knowing what naval gunnery instructors had understood for decades. This pattern repeats throughout military history. Organizations solve problems but don't systematize or document the solution in ways that transfer knowledge across domains or across time. Veterans leave service. Institutional memory vanishes. The same problem emerges in a new context and has to be solved again. The military learned this lesson partially. After WWII, there was more emphasis on documenting technical and tactical lessons, but the knowledge loss still happened in Korea. Deflection shooting had to be partially reinvented. Partially happened again in Vietnam. Leading indicators in missile effectiveness weren't initially connected to WWII defenses against gun attacks, and continues happening today. Modern military organizations spend enormous resources on lessons learned programs, formal processes for capturing knowledge after operations end. These programs exist precisely because experience shows that without deliberate institutional mechanisms, knowledge disperses when people leave service. If you're realizing that this is as much a story about institutional failure as it is about physics and training, about how organizations systemically fail to preserve critical knowledge between conflicts, hit that subscribe button right now and turn on notifications. Drop a comment on whether you think modern institutions are better at preserving knowledge than WWII era ones were. And keep watching, because the story reaches its deepest level when we consider what deflection shooting teaches us about human nature. Modern air-to-air combat has evolved to the point where guns are rarely the primary weapon. The AIM-120 AMRAAM missile operates at ranges where the target is invisible to the naked eye, sometimes 40+ miles away. The missile uses inertial guidance and active radar to continuously update its trajectory toward predicted target positions. The physics haven't changed. The missile still has to aim where the target will be, not where it is. But now computers handle the calculation, updating thousands of times per second instead of gunners estimating angles manually. The F-22 Raptor's AN/APG-77 radar doesn't just track targets. It predicts future positions based on current velocity and acceleration data, then positions the aircraft and selects weapons accordingly. Modern air defense systems like the Phalanx CIWS protecting aircraft carriers are essentially automated. Implementations of the same principle WWII gunners struggled with, calculating where the target will be and placing projectiles there. You might think this automation would eliminate the need for human judgment or training in deflection principles. You'd be wrong. Top Gun instructors still teach deflection shooting fundamentals, not because pilots expect a dogfight with cannons in contemporary air combat. The likelihood is extremely low. Modern combat happens at beyond visual range where missiles dominate, but learning to visually predict where a maneuvering target will be develops spatial awareness that applies to every aspect of air combat. A pilot who's mastered deflection shooting intuitively understands closure rates, angle off, and lead pursuit curves. These concepts matter whether firing a cannon, positioning for a missile shot, or conducting any maneuver in three-dimensional combat space. The training carries forward. It's an elegant example of how foundational principles remain relevant, even as the specific implementations change. The problem set in 1943, how do you hit a fast-moving target when physical laws require you to aim ahead of it, remains fundamentally the same in 2024. The solutions have become more sophisticated, but the core principle is unchanged. If you're realizing that a principle discovered by desperate pilots and gunners in WWII remains foundational to the most advanced fighter aircraft in the world, hit that like button and subscribe. Drop a comment on whether you think future pilots will still need to understand deflection principles even if combat becomes fully autonomous. And keep watching because the final lesson of deflection shooting extends far beyond aviation. The deflection shooting problem reveals something profound about how human decision-making breaks down under pressure in novel situations, the phenomenon that kept gunners reverting to pursuit curve logic, aiming directly at visible targets, even when physics demanded they lead, is called threat fixation. Under extreme stress, the human brain defaults to the most cognitively available solution rather than the correct one. What feels right takes precedence over what is right. This isn't unique to WWII gunners. It appears throughout high-stress domains. Emergency room physicians, under time pressure, often anchor on initial diagnoses rather than reconsidering as new information emerges. The first diagnosis feels right because it was consciously derived. Subsequent diagnoses require cognitive effort to reconsider. Under stress, reconsidering feels wrong even when objectively it would produce better outcomes. Pilots in instrument failure emergencies sometimes trust their instincts about aircraft position rather than their instruments. Their balance organs are giving them false information about orientation, but the false information feels real. They trust the feeling and crash. Traders in financial crises make decisions based on emotional responses to recent market movements rather than fundamental analysis. The emotional reaction feels more immediate and real than the analytical conclusion. This pattern appears so consistently across domains that psychologists have studied it extensively. Under extreme cognitive load, humans shift from analytical processing to heuristic processing. We use mental shortcuts that usually work fine but can catastrophically fail in novel situations where those shortcuts don't apply. The deflection shooting problem was exactly this scenario, a novel situation where human evolutionary heuristics were fundamentally mismatched to the physics. Your brain evolved to throw spears at animals moving at 20 mph. That evolutionary heritage gives you good instincts for that scenario. But at 300 mph, your instincts are not just wrong. They're 96% wrong. The solution wasn't to give gunners a new instinct. Impossible. Instincts don't update that fast. The solution was to automate the correct response through repetition until it became unconscious competence. The solution was to build equipment that could calculate the right answer faster than conscious thought. The solution was to train in conditions realistic enough that conscious thought would break down, forcing unconscious competence to take over. None of these solutions overcame the mismatch between human cognition and the problem. They worked around it. Understanding this principle suggests approaches to other problems where human instinct fails. In medical training, Rather than just teaching physicians to reconsider anchored diagnoses, create training scenarios where time pressure forces them to develop instinctive pattern recognition that catches overlooked information. RAF fighter pilots learned this from skeet shooting, creating muscle memory that bypassed conscious thought. In pilot training, rather than just telling pilots to trust instruments over sensations, create training scenarios where pilots fly in instrument conditions with realistic sensory feedback until instrument reading becomes as automatic as conscious awareness of equilibrium. Creating the discomfort of trust testing under low stakes builds unconscious confidence in instruments. In trading, rather than expecting traders to make analytical decisions under extreme stress, impossible, create institutional structures where automatic responses, algorithmic trading, circuit breakers, mandatory pauses, substitute for conscious analysis during crisis periods, the trading equivalent of the Mark 14 computing Gunsight. The deflection shooting problem was solved not by making humans smarter or faster, but by building institutions, equipment, and training systems that worked with human psychology rather than against it. If you're realizing that this story about deflection shooting is actually a story about how to work with human psychology rather than against it, and how every organization dealing with high-stress decision-making is essentially trying to solve the deflection shooting problem in different domains, hit that subscribe button right now and turn on notifications. Drop a comment on what high-stress domain you think needs better solutions to this mismatch between instinct and reality. And keep watching, because we're about to tie everything together. The transformation from 4% to 20% plus hit rates during World War II represents one of the most dramatic tactical improvements in military history. Thousands of aircrewmen who would have died continued flying. Enemy fighters that would have escaped went down in flames. Bombing campaigns that might have collapsed under unsustainable casualty rates instead reached their strategic objectives. All because someone finally acknowledged that human instinct, however strong, could be catastrophically wrong when dealing with physical phenomena that humans never evolved to handle. The gunners who learned to aim at empty sky, who forced themselves to fire at nothing visible and trusted their bullets would meet metal, proved something essential about human adaptability. We're not prisoners of our instincts. With proper understanding, sufficient training, and enough desperation, we can reprogram our responses to match reality rather than demanding reality match our intuitions. The problem was physics. The solution required understanding that problem so completely that you could reprogram human behavior to work with it instead of against it. It required training methods that created automatic competence through repetition and feedback. It required equipment that could perform calculations faster than human brains could think. And it required military leadership willing to acknowledge that traditional approaches weren't working and try something radically different. That lesson, born in blood over Europe and the Pacific, taught through the deaths of thousands who didn't receive adequate training, remains relevant wherever humans confront situations where instinct and solution point in opposite directions. In medicine, defensive reasoning about treatment options can override evidence-based protocols, leading to worse outcomes. In business, gut instinct about market trends can override data-driven analysis. In personal relationships, emotional responses can override logical assessment of situations. The deflection shooting problem wasn't unique to aviation. It was unique in being so clearly defined, so objectively measurable, and so absolutely consequential that it demanded a solution. That demand created innovations. Training methodology, mechanical computing systems, institutional structures for preserving knowledge that extended far beyond aviation. The training principles developed by the Naval Air Gunner School became templates for high-stress training in dozens of fields. The mechanical computing principles that Draper developed at MIT became foundations for modern fire control systems, autopilots, and eventually digital computers themselves. If this entire story about how a physics problem that killed thousands was solved through a combination of training, equipment, and institutional change, and how that solution became the foundation for everything from Korean, Warfighters to F-22, Raptors to top. Gun training to modern air defense systems has gripped you and changed how you think about the gap between human instinct and physical reality. Hit that like button right now and subscribe. Drop a comment on what modern problem you think we're currently getting wrong because our instincts point us toward the wrong solution. Share this video because the lessons about the importance of training, equipment, institutional knowledge, and the willingness to trust counterintuitive solutions apply everywhere. And thank you for watching how one counterintuitive technique, aiming at empty sky, doubled the kill rate of an entire generation of combat, crews, and changed military technology, training methodology, and human understanding of how we learn and adapt for nearly a century afterward.